Good afternoon, good morning, good evening, everyone. We are very happy this week to greet Jaap Nienhuis, who will bring us around the world looking at delta morphodynamics. Before we start, a few more details. We are going to see you in for the second half, essentially, of that season of Landscapes Live that marked the post EGU part. So we have Audrey Margerier next week. And of course, you might be listening to me live on Zoom or already on YouTube. And keep in mind that we have this really big and growing collection of excellent talks on YouTube about, I think this talk will be the number 102. So this is, we passed, we're in the three-digit category right now. So today, Jaap Nienhuis, who comes to us from the Netherlands, where he started actually with a bachelor and master's at the University of Twente. He moved across the Atlantic for a PhD at MIT and Hui in 2015, following by a postdoc at Tulane, a short stint as assistant professor in 2017-2018 at Florida State University in Tallahassee. And after that, he went back to Old Europe to become a professor at Utrecht University, where he has been building his lab ever since. And we are going to see quite an overview of the work that his group is leading. Yeah.
Thank you.
Take it
Perfect.
away.
Thank you so much, Luca, for the introduction, and also UI for the invite. I've been really enjoying this seminar series. So yes, I'm going to talk about global delta morphodynamics and really about the why we do what we do and also how we do those things. And this work has been sponsored by the Dutch funding organization NWO, but also NSF. And before I begin, really, I want to say that this is not just work that I've been doing, but I've been around a fantastic group of people here at Utrecht. Some I think are also in the audience, a group of PhDs and postdocs. We are in, if you don't know Utrecht, I highly recommend you to visit. It's lovely. We got canals too. It's not just Amsterdam. And what we do broadly is not just deltas, but we look at barrier islands as well. And for all of those systems and coastal morphologies, we try to kind of use models and other things to assess how they went from the Holocene and from the past all the way into the future. So we try to do hindcasts and reconstructions as well as projections of future coastal change. So a lot of the work that you'll be seeing is from PhDs from in the past, but also current PhDs in our group at Utrecht. So before starting about global delta morphodynamics, first just delta morphodynamics, why and how, right? I think you're all familiar with the impending threat of sea level rise on our coastal environments, the deltas in particular. But one of the things I think would be good to highlight is how bad we still are in predicting what deltas will look like, right? I think I'm a bit jealous when I look at the sea level rise community and how well their projections work and how well they can kind of organize their projections about into different storylines and different RCP scenarios. And we're nowhere near that capable when we look at the morphodynamics of deltas. Right, the Krishna delta, for example, we can do some projections perhaps about bulk area extent or perhaps some flood maps that don't take into account any morphodynamics. But really assessing what the Krishna delta would look like in 2300, it's still, I think, a really nice research objective to have in the coming years and perhaps decades. Right, this was illustrated very nicely by this XKCD cartoon, I think, that really highlights how difficult morphodynamics is compared to many other sciences. Right. And just to highlight the why, in addition to, of course, forecasting and wanted to predict coastal change, I think in general, I think the other reason you want to study deltas is a simple scientific understanding of river deltas. And then into the how and how we do it. In general, what we do, or what I do a lot, is linking what I call idealized process models. So models that don't specifically simulate any delta in particular, but rather use an idealized set of initial conditions and boundary conditions. And then we try to marry that with observations, both from the lab or from satellite observations. And that marrying of these two worlds, I think, that's the difficult part, and I think that's where a lot of the science gets done. But of course, you can if you're just interested in forecasting, hindcasting, you could make complicated models fit to one specific delta, and then those might not be very suitable for understanding deltas in general. Of course, if you're just interested in the second element, understanding of deltas, then you can just leave it at the idealized process models and leave your study there. But I think if you want to tackle both and tackle both at the same time, then one approach that we've been using a lot is to do both, right? Both the idealized process models and then trying to compare those process models. Even though they're idealized, I think you can compare them to observations, but that's really the difficult part, is trying to weave these two things together. So in this talk, I'll go through examples of some of the things that we've done to try to combine those two things, and why I think the global scale is very useful for that. So this is just one example of a study. This is from my PhD from a while back. And one of the things we were interested in then was the orientation of channels on deltas, right? So this is a very specific element that is very kind of striking if you look at wave-dominated deltas. So here are two examples. One where you see the channel bend in this direction, and one, of course, if you kind of twist your head a little bit, seeing how the channel bends in the other direction. So what sets this wave orientation for deltas? And I won't go into the details now. I just kind of want to highlight some of the methods and concepts we use to tackle that issue. And in this case, we used a simple one-line coastline model that uses some wave climate offshore, so different waves from different directions that then feed a longshore sediment transport by waves along this coastline that you see here in this simulation. If you also add a river sediment flux alongshore and have some rules about how channels work on coastlines, you can then see that it replicates nicely this bending of channels, in this case, into the direction of the waves, right? So this is a nice simulation, and it corresponds to some of the things that we see there. But I really think the strength here in this case is to try to not just compare it to this one delta, but then see how, if we can change some of the boundary conditions, for example, how we can replicate other deltas. So then already you want to go from n=1 in your comparison to more than one river delta in your comparison. And then I think you want to go beyond the simple inputs like wave height and sediment fluxes, and take one step further and say, how do we really understand model output? And perhaps how can we non-dimensionalize some of our model output to build a bigger framework that tells us something or explains us something about river channel orientation? So that's what we did in this paper too. We devised two non-dimensional metrics. We called it the downdrift migration index and the updrift migration index. And all of these dots represent individual model scenarios where some deltas you can see grow symmetrically. Others, they grow in the downdrift, so away from where waves come from. And others here and have this updrift migration that you see in the blue dots. Right, so in this parameter space with just two parameters really nicely broadens and tells us that we can explain a lot of the channel orientation using just these two non-dimensional parameters. And then, of course, the really interesting part scientifically is that how this compares to observations of deltas, and that's also where we see this strength come in, right? We can calculate these non-dimensional metrics also for observed deltas, for real deltas, and see where they match, right? And that's something we learn. We get some faith in the model, but also interesting parts is where they don't match and what that then tells us about these these deltas. So that marrying between models and observations we do in this non-dimensional framework, and I think that's the strength of this approach. Of course, what you can then also do is play other games, like what happens when we, for example, increase sediment supply in a delta. And you can see in the simulation, you can then see that the channel responds and changes its orientation. And you can do this space for time substitution, both when you run a simulation, but you can also use that non-dimensional framework for that, right? You can simply say, well, perhaps the Sao Francisco first was here, but then something happened and it moved into this direction, so it changed its orientation through its lifetime. So you can do this space for time substitution in this non-dimensional framework. Another example of a non-dimensional framework I've used a lot, and this is from a paper that a former postdoc, Juan Paniagua Arojavi, and I published last year, a methods paper in JGR, where we really tried to outline how this non-dimensional framework that we constructed, how that works. And this does not go specifically into the orientation of channels on deltas, but more broadly about delta morphodynamics and how we can reconstruct dominant patterns in delta morphology. Like you can see the straight shoreline here of the Eel Delta in Northern California, the Elbe estuary or strongly tide-dominated deltas, and of course the classic river-dominated Mississippi Delta. We constructed a non-dimensional framework to compare different sediment fluxes, including the sediment flux brought by the river, the tidal sediment flux, and then the wave-driven sediment flux that tends to move sediment away from the mouth of the river delta. And this illustration here is a highly schematized river mouth and shoreline, just to illustrate how these three fluxes interact. And if one of those three is dominant, then we call them river, wave, or tide-dominated deltas. And of course, if you divide them by each other, you get non-dimensional numbers again, and you make this non-dimensional framework that is this classic Galloway triangle that many of you probably know. Right, so in this case as well, we built a non-dimensional framework that then allows us to compare simulations with observations. Right, in this case, we can make analytical predictions. So this is again from that methods paper from Pani and myself. We can make predictions saying, well, if this is the amount of river sediment supply, so 10 kilograms per second is fed by the river, this is, if you look at the offshore wave conditions and tide conditions, this is how much sediment is moved by those processes. Then we can have, don't pay too close attention to these numbers, but we can make morphologic predictions, for example, about the shape of the shoreline or the width of the channel or the number of distributary channels of this particular delta. And then we can compare that to observations, right? We can go to this specific delta and look at and measure the channel angle or measure the channel widening or shoreline angle or number of distributary channels and plot that in the same ternary framework. So we can use it to assess also the uncertainty in our methods. So we can do this for this one delta, but we can do this for many other deltas, right? And that gives us, again, some confidence in our methods. And by the way, if you're like me and you grow tired of triangles, we have also a delta square for you guys, where we simply, it's a ternary diagram with two non-dimensional numbers, the river dominance ratio and the tide dominance ratio, so you can plot them as a square as well. It was actually recommended by one of the reviewers of the paper, who remained anonymous, so thank you, reviewer number 2. But it is really nice way to look at it too, where you say, well, depending on where I am in this triangle, I predict a certain amount of flow reversal in my channel or a certain amount of distributary network development. And again, in this framework, you can compare your observations and predictions for your delta. So what I showed you before was an analytical model, but you can do the same thing in Delft3D, right? A full complexity morphodynamic model that really incorporates all the different parameters and numbers about morphodynamics that you may want And this is work from Connor Broadus, a PhD student working mostly with Effie Fufula Georgiou at UC Irvine. And he ran a bunch of Del3D scenarios and Del3D simulations where you really get the full complexity morphodynamic model, state of the art in terms of morphodynamic modeling. And from those models, you can then assess where you are in this triangle and compare that again to field observations that lie closely to those deltas in the parameter space, right? And try to see where morphologic predictions align and where they don't align. And I think in both cases, you learn something about delta morphodynamics. And I think key in this case, of course, is that when you do that comparison through this non-dimensional framework, you're never going to get a specific kind of small islands or small details in deltas, or if you predict 10 distributary channels, they might lie in different locations in the delta. So you're comparing statistics about deltas broadly rather than exact locations or exact shoreline shapes from these natural deltas. So you can compare full complexity models, but you're not going to get the exact same full complexity. I don't even think that's possible with any model yet. But that's not how this framework is meant to work. And then, of course, in this framework as well, in addition to the channel orientation framework, we can do this space for time substitution. And I think really that's where this global delta morphodynamics comes in handy, because you get more and more and more data points. You get more and more certain about your model results, but also about the inaccuracy or the uncertainty in your model results. So this is within that same ternary diagram, the same framework of delta morphology, where we then extract observations and predictions for deltas and for 10,000 different river deltas around the world. The size of the circle denotes, in this case, the size of the deltas. So you see big deltas lie in this river to tide dominated corner. You get smaller and smaller deltas toward this wave dominated corner. Right, but you have many, many deltas now in this non-dimensional framework. So what you can do then is say, well, perhaps my delta is changing. Perhaps I've run a model and my delta used to be here in this river dominated corner, but now there was deforestation. There was an increase in river sediment flux that made the delta more river dominated. So it went up in this triangle. Perhaps at the same time, this delta witnessed sea level rise that reduced the amount of sediment available in the river mouth. So it quickly lowered again this position of this delta in this triangle. And in this case, perhaps it might even transition to a tide dominated corner. Other influences might happen as well. Perhaps there's increased storminess that would drag a delta towards this side of the triangle. And all of those things, of course, affect delta morphology and perhaps affect delta morphology at the same time. So there might be a net movement of the delta from this to this location. Right, so you can integrate different effects on deltas, on delta morphology within this same framework, as long as they affect some of these sediment fluxes. And then you can play that space for time game, saying, well, perhaps this delta morphology was here, but now in the future, at some point, without talking about any specific time yet, we expect its morphology to look something like this in the future. Right, so for example, the Mississippi Delta, this is what it looks like right now, and with a certain amount of deforestation, sea level rise, increased storminess, it will change to something like this. Of course, this is not reality, so please don't take my word that the Mississippi Delta will change to this, but and this is also not published, so perhaps it's more like a discussion topic for now, than whether or not it's possible. But I just wanted to talk about how you can use this triangle and this density of delta data that we have in this triangle to play that space for time game and saying, well, we don't have observations of the Mississippi Delta changing its morphology over the past thousands of years. But we have deltas that look like this if boundary conditions or if sediment fluxes in the future change in this way. So that's how you can play that space for time. So the second half of my talk, so I gave some ideas about why we do these delta morphodynamics, and I'll summarize that, and then I'll transition to how we do this in practice. So again, I think we do this global delta morphodynamics to allow for efficient space for time substitution. If we do this on a global scale, we really greatly expand our range of parameters, right? If we look at a lot of different channel orientations, we go from all sorts of angles, and by increasing the range, I think we can be a lot more certain when it comes to calibrating parameters. There might also be a smaller selection bias, right? You're not picking the ones that work or that fit your criteria of what the delta should look like or does look like according to your model. You really are quite objective, I think, in the cases you use for comparison. And because you have so much data on this global scale, you might be able to detect very subtle signals that you weren't able to detect before. And lastly, I think what is also very cool is that there might be, by doing this on a global scale, you can then also aggregate and say, well, what are global changes to delta morphology, and how do they, for example, affect global biogeochemical cycles or other elements of global change in terms of society, land use, et cetera, ecology. All right, so in this is some photos. We had a meeting a month ago or so, leaky deltas, where we tried to capture this global effect of deltas on biogeochemical cycles. So we have this nice working group now to look into these things more often. If you're interested, you can Google leaky deltas and you can find us. And please get in touch if you're interested in this kind of combination of deltas and biogeochemistry. But what I want to highlight, I think, with this list of why we do global delta morphodynamics, it's not just because it's nice to do things on a global scale, but I think it also increases our understanding of individual deltas. So that I think there are two good reasons to do this type of stuff. So then I think a nice transition to then how we do this and what are some things and ways to do it well, and how I think things should be improved in the future. And I think it's nice to illustrate it with this kind of snapshot of the Mississippi Delta, right? This is the whole Mississippi Delta. It's the fastest eroding delta in the world. And you can see this from this time lapse of the past 20 years of the bird foods, all right? So there's rapid erosion in the Mississippi River Delta, but in terms of morphology, it's not changing that rapidly, right? It's still going to be river dominated, probably in the foreseeable future or in our lifetimes. But there are other things that you might want to do. And in this case, I want to discuss a project where we were interested in kind of predicting global land loss and land gain for deltas. And also in that project, I think that the global scale really helped us, right? Because we have this, of course, this land loss, land gain of the Mississippi River Delta, but we look at other deltas. This is the Yangtze Delta in close to Shanghai. We can see very, very different patterns, right? So also not just looking at delta morphology or channel orientation, but also changes in deltas we can compare from case to case. So this is a project where we built a very simplified delta model to investigate the effect of sea level rise on deltas, and if some of these changes that we observe in deltas might be due to sea level rise or sediment supply. So what we did is we made a very simple geometric model that basically revolves around this simplified equation where we say that the rate of delta area change over time is a function of river sediment supply, so how much you put in, minus accommodation creation on the delta surface. So sea level rise times delta area is kind of a sediment volume that the delta wants to fill. If river sediment supply is greater than that accommodation space creation, then you build out your delta, then you have a positive dAdt. But if accommodation creation is faster than river sediment supply, then your delta erodes and you get land loss. And the rate of change is really modulated by the thickness of the delta or the depth of the faucet. So if you have a really thick delta, then it's very slow to react in terms of delta area. But if you have a very thin delta, it moves across. It moves very, very quickly. So this is really the main equation that forces this model. And then with the global data, so this is global delta area assessments, for example, all of these red triangles, global delta area mapped by Rebecca Caldwell and Doug Edmonds from Indiana University. And we can then simply apply this simple geometric model to all of these different delta shapes that we have. And of course, the nice thing I think comes in comparing it to observations. So we also have observed delta area change from Landsat imagery, from changes in water extent over the years. And we see again this Mississippi Delta land loss coming up very prominently, but also the land gain of the Ganges-Brahmaputra Delta, for example, or the Indus or the Amazon. So again, by doing this global scale, we have a very wide range of responses to sediment supply and sea level rise that we can then use to train our model. Or train is a big word, to run our model, I should say. And so what we did is we ran this model. We gave us predicted delta area change for, in this case, about 1,000 different deltas. Then we can compare that to observed delta area gain, right? And again, from this observation or from this comparison, you learn a lot. I think for one, it explains some of the variance. I think in this case, about 30% or 40% of the variability we could explain with this simple model. But also a lot of deltas don't follow this trajectory, right? So we get some insight into the performance of our model, but also we quickly see where it doesn't work, right? And something like this would have been very difficult if we just fit our model to one specific delta. Because in that case n is 1, we don't really have much information in terms of the uncertainty of our model. One of the interesting facts, by the way, in this case is that we see that we have a lot of predicted delta area gains around this 0 axis. A lot of predicted land loss for many deltas. But in terms of our observation, there's still not much movement, right? So that's one interesting thing I think to explore further, is why are these deltas forced with so much sediment supply, sea level rise, but why don't they change as much as we predict with that geometric model? So from this misfit, I think that's a nice area to look into further. But with this amount of data modeling, of course, we can then make projections saying, well, what does sea level rise do in the future under different climate scenarios? 2.5, 4.5, 8.5 is the kind of worst case climate scenario. We see in general, you see this trend of reddening. So at the end of the century for SSP 585, we expect land loss in most deltas around the world, right? With the uncertainty that I just talked about, right? So don't interpret any of these points as being predictions, but there's definitely an uncertainty bound around those predictions. And then, of course, we can sum these up and say, well, from our satellite observations, we found small delta area gain from perhaps 640,000 square kilometers of total delta area globally to about 5,000 more over the past 30 years, but under all sea level rise scenarios, this is predicted to decline, with rapid declines up to about, 50% of our delta area would be lost by 2300, according to these model predictions. But so this is nice, and I think this gives a lot of things that other people might be interested in, including like biogeochemists that do global biogeochemical cycles, or people that look at societal response to delta change. But there's a lot, I think, that needs to improve. For one, our land loss, land gain is still based on satellite imagery that really detects whether or not there is water somewhere. So this is the snapshot of the Ganges-Brahmaputra Delta, and you see indeed land loss, land gain in these aspects around the channel. But there are many other causes of something getting wetter or drier, climatologically, for example, or shrimp farms that are really hard to tease apart for individual deltas. So really, data quality is one thing that is sometimes hard on this global scale. Other things might be rapid morphodynamic change, which might not be a function of some of the things that we like to study, right? So this is the sitting river or estuary, I should say, in Myanmar. You see a rapid movement, probably not much of which can be predicted or explained by fluvial sediment supply or sea level rise, right? There's a lot of inherent dynamics in deltas on a certain time scale. Perhaps that would average out over decades, but I think that's also still an open question. And then the last, or not the last thing, one of the other things I think is interesting is the inclusion of time lags. So this is a paper that just got published by a former postdoc, Jaap, who really looked into this formula here of delta area change is a function of sediment supply. So if that's the case, then changes in this river sediment supply would automatically lead to changes in the delta growth rate. And in this model, it suggested that this is instantaneous, right? If you build a dam at the delta apex, then immediately you would see erosion. And there have been a lot of studies lately that give us time series, both of delta land loss and land gain, but also of river sediment supply. So he was like, perhaps there is a time lag. How do these things compare? How does river sediment supply fluctuation compare to delta area change? So what he used is a cross-correlation technique. So this is just an example where he has, well, if there is a river sediment supply and at the year 2000, it decreases by a certain extent. And if you have land area gain in the delta that you then see decrease 10 years later, you can apply this technique, find the correlation and say, well, apparently there is a 10-year time lag in the response of the delta to changes in fluvial sediment supply. Right, and he did this for 60 deltas around the world where we had good time series of both things. And what he found, I think, is really interesting. Looking at these time series of all 60 deltas combined, he found the highest peak in cross-correlation at a 6-year time lag, which would suggest that roughly for 60 deltas together, about 6 years after a change in sediment supply, you see the strongest response in changes in delta area, right? And this is for all study deltas, in this case 60, but also in decreased sediment supply, you see this 6-year time lag coming up, in this case a little stronger. So we don't have a good reason why yet, but I think it's a really nice finding that ties nicely to some of these elements in terms of, in this case, this model simplicity that might be good to improve in the future. Other interesting paper by a former postdoc, Su was published last year, was in sediment concentrations, right? That's also something we can readily observe from satellite imagery, right? This is the Mississippi River Delta with this very nice sediment plume, right? If we have a lot of predictions about fluvial sediment supply changes, delta area loss, perhaps some of that you can see in changes in sediment concentrations as well. So Su looked for, I think, about 300 deltas around the world in time series of sediment supply. And one of the interesting things she found was that actually sediment concentrations are going up globally in the river deltas, despite declines in fluvial sediment supply, right? We build a lot of dams, but apparently that has not affected or perhaps inversely affected, which would be interesting. The fluvial sediment, the suspended sediment concentrations in river deltas. So deltas are becoming more turbid. And then when we try to explain that, in this case, we didn't really find a good explanation, right? We tried to compare it to the river sediment supply decrease or increase. So if for one specific delta or river, there was an increase or decrease in sediment fluxes to the delta, would that then lead to an increase or decrease in suspended sediment concentration? But as you see, there is really not any correlation. And also in terms of land area change, we didn't find anything. So interesting trends, but unfortunately, I think something that still we don't understand yet about large-scale delta functioning in terms of sediment concentrations that we need to study further. And then I think going back to this, morphology is another interesting topic. We, of course, use this to assess land loss, land gain in river deltas. But how does that tie to delta morphology, where we kind of conveniently skipped over the fact of land loss and land gain and instead used equilibrium delta morphology prediction? So how are these two things married? And I think one very nice conceptual idea of that comes from Boyd already 30 years ago, or more than 30 years ago, where he said, well, if you are a regressive coastline, if you're building out, then you tend to form river deltas, strand plains, and tidal flats. But if you are a transgressive coastline, so rapid sea level rise, then you limit the amount of sediment available at the river mouth, and your deltas would then transition to tide-dominated estuaries or wave-dominated estuaries or barrier island lagoons in this case. All right, so what he suggested was a change in morphology due to a change in the sediment flux available at the river mouth. So we can play this game again in our ternary diagram and really tie sea level rise and delta morphology together. And where we do this for all of these 10,000 river deltas, you can see these faint arrows in the back and two highlighted deltas in the front. So for the Danube River Delta, for example, going from river-dominated all the way to this wave-dominated end, because of the decrease in sediment available at the river mouth, we expect a wave-dominated transgression, so changes to a wave-dominated delta or wave-dominated estuary. And then Niger would transition into this tide-dominated corner to transition to a tide-dominated estuary, in this case with rapid sea level all the way to 2,300. Then transitioning to something, I think that's also a kind of an open question. So I talked a lot about space for time, right? So if we know another delta that looks like the future boundary conditions or future forcing conditions, perhaps that says something about the future morphology of that one particular delta. But I think it's an open question when you can do that and whether you can do that, perhaps in which cases you can do that. So we're currently running simplified delta models. So this should be a movie. Yes. We can look at a cross-section of a delta forced by river sediment supply and river sand supply here, sea level rise over here. You can see this building out over time. Right, this delta builds out gradually, and at some point it hits this auto break, and then it retreats. Right, so I think our very simplified model is not able to capture this transition in deltas. So if we're not capturing that transition well in our linear or in our very simplified sea level rise model, can we then always do this space for time? I think that's also still an open question. One solution, of course, is to not use this space for time, but use time series of individual deltas. This paper by Doug Edmonds is really nice, I think, where he used a lot of observed delta area information from a sublobe of the Mississippi Delta, and then trained this model with different elements, different forcing aspects to really tease apart the controls on the land loss, in this case, of the sublobe of the Mississippi River Delta. Of course, for the Mississippi Delta, we have this kind of data, and that's really not readily available from any other deltas. But we have an ongoing project to try to use paleogeographic maps to tease and to get these longer timescale trajectories for different river deltas around the world to get into to see if we can use time series to better train our models and perhaps have to avoid this space for time substitution. The last element is humans. I think there's also a lot to explore in the interactions between morphodynamics and humans, also at a global scale. So we're currently updating our model to account for human-induced effects like subsidence, dredging, levees, land reclamation, and see how these affect morphodynamics of deltas. And that's one thing, what humans do to deltas. Then how humans cope with living on deltas. We're using these type of storylines, so building big walls and levees and pumps to see how humans live on deltas and decrease flood risk, something that PhD student Chiara Lush is working on right now, also at a global scale to see what our perspectives are for living on deltas. And with that, thank you so much for listening. I think the highlight, or what I want to kind of really have as a takeaway, is that we use these simplified process models with global observations. And really, I think the interesting science comes from marrying these two, which gives us both predictions about deltas, but also understanding about things that affect deltas. Thank you so much.
Thank you. Yeah, that was great. So I will let people write their questions in the chat, but maybe while they do so, Yue, would you have a question? I would have some already.
Yeah, so I do have one question actually, but you have already showed that the substance is very important, and I would like to know more about how compaction subsidence is working against sea level rise in the maybe 100 years time scale, and I mean how much influence it has, I mean compared to the sea level rise.
Yeah, that's a very good question, and I really forgot to tell that, but in our where should I go? So when we make these projections of delta area loss, it's relative sea level rise. So we have best estimate of subsidence now on deltas that we include. But we include subsidence already, but we don't have projections of subsidence. Those don't exist yet. So it might be and when we do this, we find that future sea level rise is more important than subsidence now. But of course, we don't know subsidence in the future. So it might be again that subsidence will become more important again. But subsidence is definitely a dominant control now. And
Yeah.
I think one of the nice thing of subsidence is that because it's so variable, it gives us a very broad parameter range to look into the effects of relative sea level rise on deltas.
Actually, on that slide, and I think you showed the equation on the previous slide on page 21, on slide 21, do you simply modify the future sea level to make these predictions, or is there also a modification of the river sediment discharge?
No, the river sediment supply in this case is held at what it is now.
Okay.
We have some Francis Dunn, who's a faculty in our department, has some projections of future sediment supply that it's unpublished, but there is some work to combine both supply predictions and sea level predictions. The hard thing about supply predictions is it's heavily dependent on dam building. So
right.
You need to make assumptions of which river where would build a dam in the future, and that's really a hard thing to do.
So this sort of masks any effect of the change in the climate, changing rates of erosion and delivery to the rivers. The dams are going to be really the big factors.
Yes, yes. Yeah.
All right. So no, I think you all can write in the chat. I sure hope that I allowed you correctly. Oh yes, I have the proof of it. Thanks, Benjamin Guerrero. So I'll take this question and read it out loud for you. Amazing talk, Jaap. I was wondering, how would sea level rise affect the number of active fluvial reaches, e.g. avulsions, within a given delta, and how could that affect the interaction between the land and the sea?
Very good question. So I didn't discuss avulsions, but but perhaps just not thinking about like the act of an avulsion, but thinking about the number of distributary channels. One of the projections that you have from this non-dimensional framework here is that sea level rise forces deltas to become more wave or tide dominated, especially when you become more wave dominated, you tend to silt in channels, so reduce the number of distributary channels. In addition to that, I think sea level also forces deltas into their kind of confinement into incised valleys where there's simply less space for avulsions or for more distributary channels. So I would say fewer distributary channels. But the timescales, I think, are an open question. And then definitely like distributary channels also affect whether or not you have them affects residence time in deltas. So also carbon transport, nitrogen transport, all of that stuff in deltas. So deltas as a reactor are affected by how complex the networks are.
Thanks. And it's a thanks from Benjamin as well. I was wondering, and this betrays partly my perspective from a largely land-based geologist. We often look at the ocean as a sort of a stable boundary condition for whatever happens on land. On the timescales that you're looking at, I see actually on this slide, you show an increased storminess. Is the change in wave power significant in the past or in the future projection in terms of the power of the storms?
Yeah, good question. This is of course conceptual. We did look into that at some point because there are global projections of changing wave heights. Those are typically on the order of like 5 to 10%.
Okay.
So they might matter individually, perhaps for a delta, but on the large scale, it also balances out a little bit. So some things become a little more active, some a little less active.
Okay.
So definitely compared to sea level rise, it's not gonna be noticeable, I think, on a global scale.
All right. Thank you.
Yeah.
Yeah. You want to take the next
Okay.
question?
Yeah. So we have another question from Danghan Xie. So he asks, okay, thank you, Jaap. Very good talk. I wonder if the presence of the ecological system, such as salt marsh, mangroves, will affect the transition between different types of delta you mentioned for all the tide, wave, and river-dominated deltas.
Yeah, good question. It's currently Muriel Bruckner at LSU is a student, Ander, who is trying to do that, trying to run Delph3D simulations and look at the effects of vegetation on the morphology. So, of course, this triangle that you see here is just three aspects of delta morphology, right? So things like ice or grain size or other like also vegetation are not specifically included. So they found that there is an effect in terms of how much sediment is trapped on the delta plane, how much what the elevation distribution is of the delta plane, stuff like that. So that must have some effect on the morphology too, or on the plan for morphology. Yes, but they would then plot on the same plot in this ternary diagram, right? It doesn't explain everything.
All right. The next question that we have will be from Yang Shu. A nice talk, always satisfying to see how environmental drivers could explain data dynamics. And the question is, in predicting future delta dynamics, how would you parameterize the channel and the shoreline geometry? Do you think it is more of a self-reinforcing or self-stabilizing process?
Oh, that's a good question. So what is meant? That's self-stabilizing process or a self-reinforcing.
So
yeah, I would say it's hard to know exactly. So Ian, what do you what do you mean with that? Yeah.
Yang, if you could add a clarification to be clear, in which way do you mean the parameterization of the
Yeah.
channel or the shoreline geometry? Maybe while this is being redrafted or like more precisely written, we could just jump to the next question, and we come back to you, Young, right after. Jiong Lee, representation, Jaap. For the overestimated or underestimated delta area in certain regions, for example, the Mekong or Nile, could you decouple uncertainties in your model input parameters, sediment flux, sea level rise, force and thickness, and figure out what causes these deviations?
Yeah, very good question. Right, I think we're somewhere here. I don't know. There is definitely uncertainty. You can play a sensitivity analysis, right? And saying like we of course have some way to assess uncertainty in sea level projections, and we can run the model and see what the range is. Right, and in some cases, that deviation might be much bigger. So there could be other reasons that cause that. Ideally, right, if there is some structural deviation, you would see that in different deltas too. So you could add some parameter to the model and then explain more of the variance, but then you would have to know which parameter to add or what to look for specifically. It's hard to say. I
You
don't,
mentioned
yeah. If anyone has an idea.
when you were presenting this slide, you spent a bit of time highlighting that the prediction you have prediction of more change than what is observed is
Yes,
quite a
yeah,
lot of
there's a lot of around this line, right? Especially the smaller
yeah,
ones.
they tend to be on that very little change. What would be you stopped shy of speculating a bit further about
Yeah.
those stabilizing factors, and
Yeah. Oh,
would
so yeah,
you
that's going back to Ian, right? That could be stabilizing. That could be one of the stabilizing things. So, um, um, yeah. I stopped shy because I don't know if I know.
so is
I'm
vegetation playing an important role here, for
No,
example, or
it could be that it takes time, right? So there's a time lag element.
yeah.
It could be that a certain percentage of the river discharge, so it could be some sort of buffering. If you have a lot of sediment supply, then it's simply moved to the ocean. It doesn't contribute. If you have lesser sediment supply, more is trapped. So there could be a relation between sediment supply and how much is left on the delta, which also would buffer changes. And that's not in our model, but would make the observed delta change much less than the predicted, right? If you
Right.
right,
Yeah,
yeah, I
yeah.
think good question. So
Oh,
something that buffers a lot of sediment would move away,
Would move
wouldn't
away.
lead to
Yeah,
much
yeah.
gain. If you have
Yeah.
less, then it gets to be much more efficient, so you also erode less.
Self-adjustment for stability there.
Yes,
Oh,
yeah. Yeah.
so let's go back
also we have.
to Yang. We could unmute you if you prefer, Yang. That might be simpler, but you want to read it out loud, and then we can unmute Yang for further clarifications.
Okay. So Ian updated his question. He said, we recently had a discussion on river networks and how the geometry of river junctions could appear as an optimization depending on the watershed area and climate factor. Similar thoughts are mentioned in the tidal channel networks. I think delta could be different from these systems in a way. It could be self-reinforcing. In a way, it got away to one direction of control. For example, sea level rise decrease the river control over a delta, and then there's no fight back from the river. Yeah, still very complicated to me. Yeah.
Yes. No, it's
Yang, I think you can unmute yourself if you want to. Yeah, here we are.
Okay. Sounds like my less formatted question just earned my voice over this seminar.
Yeah.
I guess I'm more trying to ask, so if we want to predict, for example, land area changes, maybe a way to do that is to model the shoreline, right? And then also where the channel will be on the delta. And instead of doing a really complicated process model, a optimization process is one way to skip over many difficult processes. And then if we can say, okay, the river delta system is trying to optimize energy expenditure along a channel or trying to optimize drainage density, and then we can reach that equilibrium vision very quickly. And that's an easy way to predict. But that's with the assumption that river delta system is stabilizing, right? I guess the question is, do you think it is a self-stabilizing system, or do you see more delta operate without equilibrium?
Yeah, it's a good, it's interesting because I think it was definitely in the kind of academia 20, 30 years ago was talking a lot about these higher order things like energy expenditure and how that would imprint deltas or landscapes in general or other things about the environment. And we kind of, I think as a community, we kind of went away again, but I don't know if it was ever solved. So it could be that deltas are optimizing something. It's hard to get that from, like, if you do a bottom-up reductionistic model like Del3D, you might see some elements of that, but how would you prove it? How would you prove that? I think it's interesting thought, and it may be there, but I don't know how to prove that.
Well, I think that's the beauty of the global work you're doing, right? Because you can have all these large-scale data sets, and maybe that's a way to prove it. If you have a geometry metrics, the golden 72 degrees of river channels, and then you find it over many shorelines.
Yeah, that's true. No, that's a good point. It's something worth exploring, I think. And it's, but also I would say the 72 in delta channel, in distributary channels there was a physics explanation for it based on groundwater and other things, if I recall correctly. And climate.
Yeah.
But
yeah. Happy to chat more.
Definitely. It'll be fun.
We can definitely start writing.
I'll mute myself now and give space to others.
All right. Thank you very much, Yang. Cool that we could clarify this. We're reaching the hour, so actually we're going to close this session. Thanks again, Jaap. That was a really nice overview. Thanks, Yue, for co-hosting with me. Before we say goodbye, just a reminder that next week we will listen to Audrey Margerier, who is going to take us upstream in the river system and upstream of the river system, talking about unraveling sediment transport and landscape evolution using trapped charge dating techniques. In the meantime, before I stop this recording, thank you, Jaap, once again. Thank you, everyone, for being here, for posting your questions, and we see you soon. Bye-bye.
Thank you.